We always start with the domain of the function. After the domain, we are going to find all asymptotes. The domain will tell us what are the possible vertical asymptotes. We still need to take the limit to check. And we also need to know what happens at plus or minus infinity to find horizontal asymptotes, if any. Then we have to do exactly as before, which means sketch a graph that does not have asymptotes. We are going to differentiate once and twice and to find the zeros of the first and the second derivative. We are going to do analysis on the real line for the first and the second derivative to find increasing, decreasing, concave up, concave down, local, max, min, and inflection points. All those are important points, and we need to find the coordinates, which mean we have to evaluate f of x to each one of those specific x's. Now we put everything together, we sketch the graph and we label. But don't forget, you first have to do the asymptotes. The asymptotes also have to appear on the analysis on the real line before you start to do anything else. Example: sketch the graph of the function f(x) equals e to the power of negative x to the 2. We are going to use this. The domain of this function are all real numbers. It's an exponential function. Because the domain is all real numbers, we know that there is no vertical asymptotes. Let's now check what happens at plus minus infinity. The limit of this function when x approaches negative infinity is 0. And at infinity, the limit is 0. We can conclude then that y equals 0 is the horizontal asymptote of the graph of this function. Now when we have the asymptote, only one in this case, we should analyze the first and the second derivatives. We differentiate once, please use the chain rule, and find critical numbers. I want this to be 0. And I get that x equals 0 is the only critical number. Second derivative, we have to use the product rule, and when we differentiate e to the negative x to the power of 2, we'll have to use also the chain rule. We will write it as product of terms, and now we want to find the zeros of this one. Pay attention that e to the negative x to the power of 2 is never 0. Actually, it's always positive. And this one is 0 when x equals negative 1 over square root of 2 and 1 over square root of 2. Now we're going to do the analysis on the real line. We will start by analyzing the first derivative. It is 0 at 0. It is plus here, so the function is increasing, and then it is negative, so the function is decreasing. And we get also that there is a local maximum at x equals 0. For the second derivative, it is 0 here and 0 here. It's plus here, so it is concave up. Then, between those 2 points, it is negative, so it is concave down, and then concave up again. And if you notice, there are 2 changes in concavity, so we have 2 inflection points. One inflection point is when x equals negative 1 over square root of 2, and the other is when x equals 1 over square root of 2. We have to evaluate the 3 important points. We'll do it by chart. The values of the important x's are 0, and the 2 values of the x for the inflection points. We substitute for 0 and we get 1. So the coordinate, the whole point, is 0, 1. Then we substitute negative 1 over square root of 2. and we get e to the power of negative 1 over 2. So the point is this. And then we substitute this number, and we get that. Now we're also going to sketch the graph. So we're doing again everything in parallel. The first thing to put on the graph is the horizontal asymptote. It's y equals 0. On purpose, I have it only as a dotted line on the sides because this is the end behavior. This is only when x approaches infinity and minus infinity. Now I can put those 2 points just to help me to find the shape of the graph. And here I know that the function is increasing and concave up. Then it is increasing and concave down. Here it is decreasing and concave down. And here it is decreasing and concave up. I have the shape of the graph now. I have the 3 points to kind of guide me. And don't forget the horizontal asymptote. If you also look at the function is always positive because it's e to the power of something. So all this function is going to be above the x-axis. When I incorporate of that, I'm getting that this is the graph of the function. If you notice, you see that we get actually a graph of an even function because there's a total symmetry with respect to the y-axis. And indeed, if you check, e to the negative x to the power of 2 is an even function. Example, sketch the graph of the rational function f(x) equals 2x minus 1 over x plus 3. The most important thing is first the domain. The domain of this function are all real numbers except that x cannot be negative 3. We start with the asymptotes now. We have to check x equals negative 3 to see if this is a vertical asymptote. We are going to take the two-sided limits when x approaching to negative 3 from the right and from the left. From the right, we have to do really quickly this mental work. It's negative 3 plus for the x plus 3. Negative 3 plus is negative 3, but just a little bit more. So when you add 3, you're already crossing to be in the positive side. So it is a 0 plus. On top, we can just substitute negative 3. And we get negative 7 over something very, very tiny but positive. So this is a quotient of negative over a positive, so it's a negative. And also it has to be infinite. And we get negative infinity. Let's take also the other sided limit. Even though we know already that this is a vertical asymptote, I mean x equals negative 3, we want also to find the other limit because we need to sketch the graph and we want to know what to do. And when we do now the mental work, we know that negative 3 minus is a little bit less than negative 3. So when we add 3, we are still in the negative territory, which means that it is 0 minus. On top is, as before, negative 7. And we have negative negative, so it is positive, and also it's infinite. And we get infinity. We conclude then that x equals negative 3 is a vertical asymptote of the graph of the function. Now we need to find the horizontal asymptotes. For this, we will need to take the limit of the function at plus minus infinity. Well, we can use L'Hopital or you can use any other method. The limit when x approaches infinity is 2. This is a rational function, so it has to be also that the limit when x approaches negative infinity is the same to the limit approaches to infinity, which is 2. Again, you can use L'Hopital or dividing by the highest power of the denominator, which is x, whenever you like. But the conclusion is the same, that y equals 2 is horizontal asymptote. Now we need to analyze first and second derivative. Here is the first derivative, and here is the second. If you notice, the first and the second derivative are never zero. Now we are ready to do the analysis of the real line for the first and the second derivative. And here is the most important issue. You have to put the asymptotes before you start anything else. Definitely the vertical asymptote. The vertical asymptote is x equals -3, and you have to put it in your chart because the vertical asymptote actually dividing the graph of this function to two different graphs that are gathered together. We have to get here two parts, one from the left of the asymptote and one from the right of the asymptote. And I would like to recall, you never cross vertical asymptote. X equals -3 is not in the domain of the function. We're also going to sketch the horizontal asymptote y equals 2, and again, it's only minus plus infinity. It's not in the middle. And in this case, they are not really important points. If you want, you can find maybe the intercepts. You don't have to, but you can if you want. We check. Here it is a plus. You can take a sample point like -7, but it really doesn't matter. If you look at the first derivative is a positive number over something to the power of 2, which is also positive. It means that the first derivative is always positive when x is not -3. We get then that the function is increasing here and it's also increasing here. But pay attention, you cannot cross x equals -3. So it's wrong to do one line of the function increasing. Those are two separate parts of the graph. What about second derivative? Here, there is a change in the sign at x equals -3. So we have to take a sample point, and we get that here it is a plus, so it is concave up, and here it concave down. Pay attention, x equals -3 cannot be the x-coordinate of the inflection point because it's not on the graph. The graph here that you can see has no local min and max and has no inflection points. And this is the graph of the function. Again, if you like, you can really easily calculate f of 0. This is just going to help you a little bit with sketching the graph by knowing the intercept. If you plug 0, you get that f0 is -1/3. And there's nothing really to label here because, again, there are no local extrema and there are no inflection points. We can check now also all the limits that we had calculated before. You can see easily, for example, that this is a vertical asymptote, but also the limit of the function from the left to this asymptote approaches infinity. And from the right side, it approaches -infinity. Y equals 2 is a horizontal asymptote, and indeed I would like to recall that the limit of this function when x approaches -infinity and at infinity indeed approaches 2.